In this video, we will clarify the terminology of centripetal force and acceleration, and how they are placed in the rotational quantities system. Let's first recall how we get this type of force and acceleration. Converting linear motion into rotational motion can be done by applying a force perpendicular to the direction of motion. In a circular motion, this perpendicular or orthogonal force has a constant magnitude and is always directed to the axis or center of rotation, which makes it called centripetal force. Let's recall the result from derivation of rotational quantities in the last video, which can be summarized in this table here. Where should we place the centripetal force and acceleration on the table? Centripetal force in a circular motion is both radial and orthogonal. Because its direction is along the radius of trajectory, while simultaneously also perpendicular to the direction of motion. They are counterbalancing, which leaves the rotational radius unchanged. Among these type of quantities, only the radial is perceived in the rotating reference frame. The other types are perceived in inertial reference frame. That's why in a circular motion, radial acceleration is 0, while the orthogonal acceleration is not. You might be wondering why the units for radial force and orthogonal force in this table are different from the units commonly used for centripetal force, which is also used for linear force, which is Newton. Orthogonal acceleration even has different unit from radial acceleration. Both are different from the units commonly used for centripetal acceleration, which is also used for linear acceleration, which is meter per second squared. To clarify these differences, let's analyze a simple experiment shown in a moment. Centripetal acceleration can be calculated as tangential velocity squared divided by rotational radius. It's also equal to angular velocity squared times rotational radius, which means that it's equal to tangential velocity times angular velocity. Thus, its proper unit should be meter radian per second squared. Centripetal force is mass times centripetal acceleration. Its proper unit should be kilogram meter radian per second squared. Let's verify that the unit for centripetal acceleration is indeed meter radian per second squared. On the left-hand side, the ball has tangential velocity of 1 meter per second. Its angular velocity is 1 radian per second. The length of the string is 1 meter. The ball gets centripetal acceleration of 1 meter radian per second squared. On the right-hand side, the ball has tangential velocity of 1 meter per second. Its angular velocity is 2 radian per second. The length of the string is a half meter. The ball gets centripetal acceleration of 2 meter radian per second squared. Thus indeed, the value of the radian affects the value of centripetal acceleration. In a circular orbit, tangential force is 0. Radial force equals orthogonal force. In an elliptical orbit, radial force equals vector addition of tangential and orthogonal forces. At aphelion and perihelion, tangential force is 0, which means orthogonal force equals radial force. Centripetal force is a special case of radial force, which is often introduced using an experiment with a small ball attached to a string. But this example severely limits the possibility for other values of radial force. Here's some other possible values of radial force, when the string is replaced by a piston or linear motor. This change makes it possible to do work on the revolving ball. If the radial force is larger than orthogonal force, the radius is reduced. The piston is contracting, and it must do some work. If the radial force equals to orthogonal force, the radius is constant. Thus, there's no work. If the radial force is less than orthogonal force but still positive, the radius increases. The piston is passively expanding. It can be used to extract some energy. If the radial force is 0, the radius also increases. The piston is passively expanding, following the linear trajectory of the ball. It cannot be used to extract some energy. If the radial force is in the opposite direction, the radius increases even more quickly. The piston is actively expanding, and it must do some work. The last case shows that centrifugal force isn't always fictitious. It can also be real. The launching of spacecrafts is another example in this category. Let's analyze the work done by the system in this scenario. The radial work is the integral of force with respect to radial displacement. Its value is positive as the force is in the same direction as the displacement, and negative if they point to opposite direction. It's 0 if either force or displacement is 0. When the radius is decreasing, the radial force is inward. So is the radial displacement. Since they point to the same direction, the work done is positive. Thanks for watching. Don't forget to like, comment and subscribe.